and welcome to the third installment of the Essential C Security Lecture Series, part of the Offensive Computer Security courseware hosted at hackallthethings.com. The topic of this lecture today is polymorphism and type confusion vulnerabilities. Technically, it's mostly just C++. The outline of this talk is first we're going to spend some time going over the background information you need to know to understand type confusion bugs, which means polymorphism and understanding how dynamic polymorphism works and other runtime security checks. And then finally diving into the very, very powerful type confusion vulnerabilities that plague major projects today and the techniques that are used to exploit them. Now, we've covered a lot of C topics so far, and if you are at this point confused, good. That's totally fine. Security is not intuitive. It is absolutely not intuitive. And we're about to dive into a class of bugs that occurs only when the language itself is confused. And for you to be confused, that's totally natural. There's some really powerful vulnerabilities that have been found in the last 5 years that are type confusion bugs in major projects like browsers, operating systems, and etc. It is today now a major vulnerability category. It occurs only in large object-oriented projects that involve different modules, whether they're DLLs or shared objects, and libraries that are doing all sorts of different things, like handling media formats, handling rendering, handling Flash, handling etc. And they're passing back and forth very complex binary formats in terms of data. So this encompasses browsers, operating systems, sandboxes, virtual machines, and etc. And specifically, type confusion vulnerabilities occur when a pointer points to an object of an incompatible type. So let's first cover some terminology. When assigning a value to a pointer in C or C++, the developer has a particular object in mind, and it is termed in general the intended referent. This term, the intended referent, will be used multiple times throughout this lecture, and is one that you should take note of. Array accesses also follow this terminology as well. The bracket index notation simply just means that the intended referent is the ith or nth member of that array of objects. Anyways, back to the subject. There are a number of both compile time and runtime strategies to ensure that when a pointer is assigned or when something is cast, that it points to a valid object. In other words, it tries to validate the intended referent. And in the cases where this is a false positive, those are very interesting vulnerabilities. So, there are a vast amount of compiler performance evaluation research papers that you can find about compiler security strategies in this topic, but I digress. So let's cover some really basic compile time examples. These are, bugs that will keep you from compiling your code. So these simple compile time examples, let's start with the first one. We have a class A and a class B that inherits clearly from class A. And we declare an object of type class B and we try to cast it up to the more general case, class A. This is a pretty standard error that most developers should be aware of when they're first playing around with C++. If it is an incompatible cast, this will be thrown. Secondly, those who have toyed around with the C++ style casting types, such as static cast, dynamic cast, will also encounter such errors when trying to do similar operations. But these can be determined and resolved at compile time. There are other types of issues that simply cannot be determined at compile time, such as doing um, array access for the intended referent. It is sometimes, in some cases, impossible to determine if this goes out of bounds of the intended referent object. In this case, if it's an array of objects, there's no determination in this code or consideration for it going out of bounds in respect to y or x object arrays. And similarly, having a just raw pointer to an object and incrementing it by 1 at compile time, this will always be deemed valid. Now, at runtime, there are a number of strategies, but we have to really dive into how polymorphism works in order to understand these. But what you need to know at this point is that runtime strategies are primarily facilitated by constructors and destructors. These are things that are present in every object, every class, and they mark the beginning and the end of an object's life cycle. When something goes out of scope, it's declared as a local variable. Once that epilogue hits, the garbage collection will be triggered. That's what we've all been taught, at least, and that's what I assume is still the case. But I digress. Polymorphism encompasses all of the following topics, from object-oriented programming to inheritance to typecasting to function overloading, overloading operators, overriding functions, overriding operators, templates, and etc. Having default values for function parameters and so on. However, in C++, many objects and variables are assigned values actually at runtime. And that's, depending on user input and etc. So, resolving what the object's variable or data type is going to be, what it inherits from, any other dynamic typecasting issues, these all have to be performed at runtime. And here's a nice little list to break it all down. The difference between static polymorphism and dynamic polymorphism. Think of static polymorphism as all the compile time issues that are solved. This is what you would think of as traditional C. And conversely, the dynamic polymorphic issues are ones that are resolved at runtime. So for the left side, we have static cast, which involves no runtime checks at all. It is a compile time decision that determines whether or not the intended referent is actually valid. Compared to here, dynamic cast, which involves checks that are built in by the compiler to run at runtime to determine whether or not the intended referent is a valid casting choice. And this is problematic. The checks here, depending on how complex the project overall is, if it's the case of a browser which has thousands, if not tens of thousands of lines of code in it, could be totally insufficient by default. The other issues at hand are function overloading, which is also paired with operator overloading, which involves primarily having default values in the function parameters, or having different types of values depending on how you want to perform that function on the input, and etc., compared to everything that falls under the umbrella of inheritance, with function overriding and operator overriding, involving overriding same named functions in the parent and base the parent and child classes that would otherwise collide in their signatures. And by signatures, I mean what is evaluated during runtime for determining how to call these things. Secondly, templates having default values and objects and etc. versus, well, not a true versus here. These are totally separate. Virtual member functions, which generate vtables and vpointers, and we have a few slides to cover those. So, dynamic polymorphism requires dynamic dispatch. Static polymorphism is something that's solved by static dispatch. The dispatch is simply the selection given a pointer assignment or a cast of an object or some other polymorphic runtime issue. It's important to note that this in implementation possibly differs on a compiler basis. Each compiler may do things differently. And the way these runtime decisions are handled is by something called runtime type information, or shorthand RTTI. And if you've come through a C++ course in college, I'd very much expect you to be familiar with RTTI. If not, your professor probably did a poor job. So, these involve symbols that are embedded throughout the binary for the program, and they involve class names, function names, virtual function names, class member variable names, and etc. And there is interesting undefined behavior that occurs when the RTTI is incorrect. More specific than undefined behavior is that it can generally lead the dynamic dispatch decisions to select wrong objects, which in turn allows for the wrong functions of a object to be called, which is one of the many ways that type confusion vulnerabilities are actually exploited. Or perhaps it leads for the wrong vtable entry to be called if that object has virtual members. So, as part of this class, you always have to think about, so what could go wrong? You'll thus, to be able to answer that, have to know to ask, how do you make this go wrong? So this is something that could go wrong. How do we make this happen? How do we understand how this can go wrong? So let's look back at this breakdown, right? And look at all the things on the compile time and all the things that happen at runtime, and try to brainstorm some ways. Feel free to pause the video at this point and brainstorm on your own, because I'm going to posit some suggestions that this could occur, that we could pollute or corrupt the RTTI. One way is perhaps by mixing static and polymorphic features on both sides, just mixing and perhaps abusing these. Or maybe heavily mixing just all the dynamic polymorphic features. Maybe the runtime security checks and compiler checks won't be able to keep up. Or maybe by abusing casting and improperly casting things. Or maybe inheriting from multiple classes and mixing the inheritance, especially when they have the same function names. If you've thought ideas that are related to any of these questions, then good, you're on the right track. If not, it's okay. Security, especially offensive security, is not intuitive for most people starting off. It's especially not intuitive for anyone who's come from a very, how do I say, very formal computer science background or very formal engineering background. The mindset is almost diametrically opposed in the intuition and the subconscious thought process that is ingrained through these training programs, both computer science degrees and engineering degrees. They don't go about taking breaks at each milestone and asking, okay, so how does this fail? And how does someone maliciously cause us to fail? And that obviously requires having the knowledge to be able to answer those questions at each stage through the life cycle of complex problems, which requires very, very deep and broad knowledge base to answer these questions. But I digress. So, for the rest of this lecture, we're going to explore a lot of hands-on examples, and it's not going to give you the answers to how we corrupt runtime type information uh, up front. Instead, we're going to explore a number of cases, help develop your intuition so that you can critically think about this stuff at very low level, in terms of very low level code at the assembly level. And that is absolutely necessary. You have to have an extremely concrete and solid foundation for this stuff because you're trying to understand how to exploit the cases and how to protect against the cases when vulnerabilities rise, when the language itself is confused about dynamic polymorphic issues. The only two tools we will use is the C++ compiler and the wonderful resource at gcc.godbolt.org. So, a quick example. On the left, we have some code illustrating function overloading. It occurs when two or more functions in the same scope have the same name. In other words, have the same signature according to the dispatcher. Now, they may have different arguments or a variable amount of arguments and so on, and determining which one is called is a compile time issue. Now, overwriting is a runtime issue, and it pertains specifically to inherited functions. But there's an important thing to note. This changes in nature when it pertains to virtual functions and virtual methods of classes, especially when there's inherited classes. So, another example to cover, or case rather to cover, is multi-level inheritance. You have class A, class B derives from A, class C derives from B, and this can go on infinitely without error. And we see that when C is instantiated as a class C and it calls a print function, it works up the inheritance chain to find a matching class, and it goes in order of most specific, so it starts with C first, then B, and then sees that it is declared in the base class. And when there's instances of ambiguity, as is illustrated on the code example on the left, the dispatch will resolve the ambiguity by picking the most specific instance or signature for the intended referent. So here, when c.print is called, it would first check C, it will recurse up the inheritance chain 1, check B, see that B has a signature for print, and the dispatcher will select it. Now, there are cases where you can inherit from multiple base classes, multiple parent classes, and this can also cause ambiguity. However, this is a compile time issue that will prevent the code from becoming compiled. There's a scope operator to resolve these cases of ambiguity. It's colon colon or double colon. Anyways, you simply say the object dot whichever base class you wish to resolve to, and then access the given function that way. And there are two ways to do it. From inside a derived class, that would be inside the class itself, or outside of it from an instantiated object. And this brings us to casting, probably the most important topic of this lecture. And if anyone's come from C, they're familiar with the C-style casting, which is technically not C++. Anyone who's been taught C++ properly would have been told this. There's static, dynamic, const, and reinterpret cast, and we're going to go over those. And these are the ways C++ handles changing the type of an object or a pointer. And for static cast, it would be static underscore cast with the intended object type, and then the pointer that is being assigned, it returns a reference to it as well. So this is for when a developer knows exactly what they're doing. It involves 0 runtime safety checks, and it is an interesting case to consider for type confusion. Dynamic casting only works with the runtime polymorphic types that we've covered so far. So anything with virtual functions, virtual methods, etc. And the notation for all of these is exactly the same. In the brackets is the intended object, and then the pointer, the variable being assigned or casted, rather. And this is reserved for when the developer does not know what the object type is going to be at runtime. It could be for a very large system, very large project, and it's common in such cases. There are other cases. Constant cast is for adding and removing the constant property. It's not very dangerous. I've never seen a vulnerability involving it. Reinterpret cast is very interesting. It converts between types by, at runtime, reinterpreting the underlying bit pattern. Yeah. There's more you can read about it. There's a good blog post here that I linked to from Hexrays, the IDA Pro developer guys. They complain in this blog how bad casting is abused as a means for documenting source code, but also introducing unintended vulnerabilities. But I digress. And the point is that any sufficiently experienced C++ dev has either done or seen someone just void casting a pointer to get past a compiler bug. And the problem with that is that void casts using either standard C casting or static, dynamic, reinterpret, etc., it actually disables the safety checks that the compiler would otherwise build in. And this is kind of like a cheap hack to get past the compiler issue at the time. And it's still done in very, very large programs. And a notable bug was a 2009 major vulnerability that I think hit all versions of Windows, and they had to roll out a emergency ghost patch to fix it. And it was a type confusion bug. There's a blog post here explaining it. So there's some general rules the developers should follow when they're doing any form of casting. You can read about them here at c++.com. But the three main ones that have security implications is that null pointers can be converted to pointers of any type. It won't throw errors if you're actually trying to use a null pointer to do something like this. Furthermore, a pointer can always be cast to a void, and a void can always be cast to anything else. As for upcasting to a less specific class, this can be done in most cases, let's say with dynamic cast, so it's doing runtime checks, where it appears that the less specific or base or parent class doesn't have any conflicting signatures that would throw off the dispatcher. Here are some code samples that I highly suggest you access and pull up gcc.godbolt and go through this code. It's really useful to go through these examples and figure out exactly how these are translating in assembly. The aspect we're looking at here is this is a multi-threaded producer-consumer program, and what's happening is that this is the function that is spawned when the thread is created, and it takes a void argument, which is very, very common in threading, and it is just C-style casting it and calling a run function, which would be here, and that will print, and on the right is what it compiles to. And so you can track at the assembly level how this cast works, and we have a separate example for static cast, now adopting C++ style casting, and you can see how this translates in the assembly over here. Down here, it's all the way at the bottom, I think. Close. There's the run function, and here is thread func. So going back to the C-style cast, you can compare the two. So now that we have the static cast version and the C-style cast version and the corresponding assembly side by side, we might ask ourselves, well, given this is a C++ style cast, we'd expect it to look a little bit different in the assembly, right? So how would we go about that? This is all perhaps Greek to me if I were a newbie looking at this. Well, run is called here, and run is the code that's right after the static cast, and it's the same case here. So we can go from run and look backwards at how this works. And if you just flip between the two, you can see that there is actually no difference, which may surprise you. But keep in mind that this is done at compile time, so any decisions in code that are invoked by static casts aren't necessarily rendered into the output assembly. So despite the fact that static cast goes through a bit more checks than just the standard C-style cast, you will not see the difference between the two rendered in the output binary. Just a neat thing you can learn by playing with code in this way. And this is a style of learning that needs to be encouraged more often, because we can go now at the assembly level and see that it is indeed not making any runtime checks. And as a side note, too many times in the field of security, there are just general claims about certain things being secure or not secure or being ownable, and it turns out the person making the claim didn't do their research, but it gets accepted because people don't verify these claims. It's very, very common. You'll see things all over Reddit all the time in the field of security that make wild claims and don't really get called out. But I digress. Let's move on and cover the more interesting aspects of static cast. By design, it is claimed to permit type confusion errors for the following two reasons. One, it allows you to convert a pointer to a base class to any derivative class, even if it's unsafe. In most cases, depends on the compiler there, however. And two, as I've said before, that it allows you to convert to or from any void pointer, and doesn't complain about this. Casting through a void pointer often disables all compiler level safety checks on an object. Now, these 2 points come from this wonderful table It's from Georgia Tech researchers David Dewey, Jonathan Griffin. Static detection of C++ vtable escape vulnerabilities in binary code, and here's a link to it. Here's also the sample code if you want to compile it. And let's just walk through it. We have two classes. They have virtual functions, so they are polymorphic objects, and class 2 derives from class 1. It also adds on two virtual functions in addition to it. What is happening in main is that class 1 is instantiated at C1. C1 calls two functions, add, node, and print, that belong to the base class, and then it is typecasted through static cast to the derivative class to call the debug function. This act here is actually a type confusion vulnerability that in this instance should segfault the program. That is under Visual Studio and G++, according to the researchers. The single line of code here causes two effects. One, we're casting to an incompatible derivative class, and two, by on the same line of code calling a void function, if you want to do safety checks of the return of static cast, you won't be able to. If it returns a null, it will be null dereferenced in an attempt to execute or call the debug function in respect to that pointer, and will obviously segfault. Now, this is twofold in bad practice. And what it actually is going to cause is a failure of casting to class 2, and instead it will dereference class 1 and try to access debug with respect to it in the vtable. Now the vtable here is listed on the right, and this is provided again from the paper. And this is a product of G++ and similar in Visual Studio. Other compilers may do this safely. Anyways, what is going to happen is that vtable for class 1 only has two entries. See these DD offsets? Each one of them is an entry. It's going to fail to do this cast and return instead a pointer to class 1, and the dereference at this level will access the fourth member here, escaping the vtable. Now, you may think that this is obviously just going to be some data. It's not going to include instructions or a pointer to something else, and that is correct. However, it is very common in memory for there to be more than two classes, and there will probably be some class, some vtable after this in memory that you can escape from this object to the next and perhaps call an unsafe function. And that is at the heart of how some type confusion vulnerabilities are exploited. In other cases, they can run unsafe functions that perform operations on the data on the stack in a manner that causes further memory corruption, and so on. It may surprise some to find out that the C++ documentation on many websites actually omits discussion of this behavior of static cast and other casting operations, especially how void disables safety checks on the intended referent assignment. Here are a number of links. Again, this claim is also from that paper, and it faults the devs for kind of indirectly causing a lot of this bad behavior, or at least bad practices in terms of static cast type confusion vulnerabilities. Here is another bug. This is a recent 2013 vulnerability in Firefox. It is 4 lines of code, and to walk through it, what is going on is there is a static cast of just a general SVG element, and they're accessing multiple functions in reference to it. Now, what the attackers did to exploit this is that although this is a base class for multiple other ones, it is a derivative class for even more generic classes. what they did was created or allocated just generic HTML element instances, and downcasting from an HTML instance to an SVG element instance would be an incompatible downtype, but it was one that's permitted at runtime by this line of code. And they have an interesting write-up here on how they went about exploiting the vulnerability and getting code execution in Firefox browsers. And it was about 3 stages, and there's a summary here. First, again, they created an HTML element and tagged it to appear to seem like an SVG tag, although there are no runtime checks being done really in Statacast. However, that doesn't preclude there being developer checks to prevent the Statacast from operating incorrectly, which in this case there were some developer built-in checks, which is the reason they went about the following kind of convoluted steps. They specifically crafted the tag to be invalid so that when the renderer parses through all the elements in the HTML file, it will not know what to do with it and instantiate it as an HTML unknown element. Now, the odd thing about HTML unknown element class is that it is recognized as a valid SVG element, and that edge case allowed them to shoe this in as a considered valid SVG type to exploit this type confusion vulnerability. Now, a second aspect of HTML unknown element that made this a good choice for the type confusion exploitation is that it's a very similar footprint in memory to a valid SVG object, and that means that the two classes have very similar structure and similar or same amount of variables of the same type, which allows the attackers to populate in memory the structure for the malicious HTML unknown element to parse at least somewhat validly as a valid SVG object, because it's going to be accessing SVG specific attributes of that object and etc. Now, the second step is not necessarily heap spray, but another technique known actually technically as heap feng shui is, instead of just brute forcing all of the objects onto the heap in the manner that hopefully causes it to be reliably exploitable, is instead doing much more fine-tuned crafted allocations and frees of heap objects in a manner that will manipulate the various free lists and fast list bins to be in a desired state to attack. And finally, when they execute the vulnerable code path to trigger the static cast, the dereference here to tree scope and get element by IDs will access, with respect to a vtable, elements that are in reference to the original HTML unknown element class, which is furthermore populated by attacker code that has been put there in memory. Now, since this is a browser bug, this is all rendered in HTML and JavaScript, and that's how they're controlling it, with at least controlling the heap. So hopefully that's not too confusing. It is a really simple type confusion vulnerability on a major target, Firefox, and pretty simple instance of it in terms of how difficult it is to exploit. There's more you can read on how Statacast works. This reference enumerates the 10 cases where Statacast will succeed, and you may be able to find more instances outside of it that are interesting, perhaps vulnerable cases where it will instead fail. Anyways, moving on. Dynamic cast is another interesting case. It is specifically for polymorphic objects, so classes that have virtual functions. Um, and it is reserved for cases when the developer does not know what the intended reference type is going to be at runtime. That may be because it's a complex program, working with user input, working with input from a web server, working with input or from somewhere else over the network. There are a few rules that pertain to dynamic cast. Namely, it has to involve polymorphic objects, at least for the base class. That the the source class, is, as far as that is concerned, um, and converting from any class to a base class or parent class is always allowed in terms of dynamic cast and casting. And it's usually used, however, in bad practices that open up vulnerabilities. And we'll dive into that. When it is called and isn't checked, it may return null, or it may return the original object, and the runtime type information will be wrong. So calling it in this manner, such that on the same line you're invoking a function call that's part of this destination cast object, can be a null pointer dereference, which on most systems will segfault. On embedded systems and mission critical systems, it may actually be exploitable because the null page is often mappable. In other words, you can write stuff to the null address. Now, similarly, casting something through void will disable all the safety checks involved in this, and this is both of these instances are very bad practice. Now, this is something I encountered as a recommendation in a programming textbook that is started in 1996, has been through 28 editions as far as I can tell according to Amazon, and there's a link to this code here, and it's advising the adoption of what a lovely slide. It's advising the adoption of using dynamic cast on objects passed to it in terms of this as a constant void, and to a constant void just to get the raw address so it can pass it to free in terms of an overall scheme for managing heap objects, which if you've gone through the heap stuff I've covered so far, this just sounds like a terrible practice that can lead to just all kinds of mistakes. Now I'll click on the link so you can see that it indeed is in this textbook. Let's see. Yep. More effective C++, 35 new ways to, yeah, perhaps not so much. And this is the short code snippet captured on these 3 pages. You can pause the video and go through it, but again, it is intended for maintaining objects on a heap to free them by their raw address, not the pointers themselves, which sounds like a disastrous approach and is probably something that has inspired multiple vulnerabilities in itself. It's just another case in the endless problems that textbooks end up causing, in my opinion. So here's how dynamic cast should be done right. When you call it, either beforehand you check the type ID of the object to make sure that the intended, destination matches up, and then you try the dynamic cast to make sure it works. That's one way to do it. It's a little bit more verbose. A simpler approach is to, after you perform the dynamic cast, is to check the object after assigning it to make sure that it is not null and then attempt this. You can furthermore check specifically that it is not null and also is of object type to carry on. Now, the main reasons dynamic cast may fail to pull off the cast is developer error or malicious inputs. The impact is that it may return a null pointer in the case of failure, but it also throws an exception, std bad cast. Um, so if that's caught, it's usually not an exploitable case. It may cause the program to crash if it's not caught, though. So this is the same code as before. What's been changed is instead of static to dynamic. Why don't you pause the video and think about what would happen, what would go wrong if this failed to cast, and in what order. So it may return a null pointer, and dereferencing a null pointer to call debug with segfault, but it would also call throw the bad cast exception, which is not going to be caught here, which would also cause it to crash, but a not exploitable way. Now, reinterpret cast, this one's good. This has been a historical culprit for many type confusion bugs. It tries to, at runtime, convert between types by reinterpreting the underlying bit pattern at the object level. And there's another caveat with this one is that it will allow the conversion of null pointers. So if a pointer is cast and then passed along and as input to this, and it was actually rendered null at some point, it will accept it as valid input. And that is interesting. So, hold on, let's rewind. Static cast, as I said, may return null. So specifically, if you static cast something, it fails, and you end up reinterpret casting it, it will be valid input, and it will proceed to typecast it, which can have disastrous effects. So here we have two classes, widget and other. They both have the same footprint in memory. They have a constructor, destructor, and a pointer to a function, which is also the same size as an integer, at least on a 32-bit system. So on a 32-bit system, these are the same. This would have to be long, or double to have the same footprint on a 64-bit system, because we have the constructor, destructor, and a pointer-sized object here. And we declare O as other, and we reinterpret cast it as widget. And it would allow this. This would be very unsafe. And this code is from Chris Rolfe's Black Hat webcast series from last year. And again, it tries to do this by reinterpreting the underlying bits. Here's an example of it being done wrong. There's a function f, and this is reinterpret casting it as a void function instead of an int, and calling it then afterwards would result in undefined behavior. But in this example that's listed, I found online, and it seemed quite egregious. And done right is maintaining the original type. But yeah, sometimes that's not always possible. So, to summarize, I'm not going to cover constant cast because that just adds and removes the constantness of a variable's type. Casting a pointer through void in any case will disable all compiler level safety checks on that object. We covered the compile time safety checks. There are some other runtime safety check strategies that have been introduced over the years, and I'm going to break them down into three categories. There are probably more. I don't feel like covering them. These touch on the major compilers. Obviously, you see Visual Studio is missing here. Too bad. Um, so we have intended referent via object tables. That's how one validation scheme is for making sure that the destination object of the type cast is valid. Intended referent via validation via shadow memory copies, and then intended referent via pointer tables. So there are a number of actual algorithm libraries that perform this in real compilers. Safecode is a big one. Mudflap is also a big one. Address sanitizer, softbound plus CETS are all examples of these systems. So the way intended referent validation via object tables work is that whenever an object goes through its creator or destructor, the object table is updated with the base address for that object and the limit, in other words, the end of its footprint in memory, is all registered in object table, and the object's address range is used as an index into the object. So any pointers that point to this range are then having their values uh, used as the lookup key for this table to validate the intended referent. So when they are deconstructed, they are freed. Now, obviously, this does not protect against uninitialized pointers, valid malicious objects, which are very common, void pointers, and some cases of misaligned pointers. There's also cases where pointer arithmetic, like having an array, will fail in this scheme, or may cause false negatives when it happens to be multiple objects back to back, say like in a vtable, and you escape the object or go past it to access another one. Some versions, however, of I think it is, let's go back, Safecode implement that correctly, as I believe. I'm not sure though. So, the way intended referent validation via shadow memory object copies works is that every time something is created or destroyed, an exact replica is created. There's a 100% memory overhead, in other words, in something called shadow memory, which is just another memory segment that keeps track of things and has a virtual addressing scheme to map directly to how it should work in the actual memory. So, when the object in shadow memory is copied, it's kind of like a taint tracking system. It marks all of those things as valid and marks them as invalid when it is destroyed. Now, intended referent validation via pointer tables works very similar to object table. It uses the pointer's location as an index to the pointer table. And this is on a per pointer basis. So whenever pointers are created, they are registered with this pointer table. And so the location of the pointer, again, is the lookup key in this pointer table. Not anything stored in the pointer. Doesn't care what the pointer points to at all, ever. But stored in that table is the object's, information. So whatever it first points to, the metadata about the base address there and the object's limit adder is staved in this table. It's a different way of doing it. It's kind of the inverse approach. It has finer granularity and also is quite faster, which I found surprising. I'd expect something built into the constructors and destructors to be faster because there can be n times more pointers to an object than the actual instance of the object itself, which means that the overhead here would happen more often. But according to the performance evaluation experiments, this is actually often 10 times faster than the object table's approach. Now, the main drawbacks is that many pointers aren't stored in memory. They're just simple registers like ESP and EBP are the main examples. EIP is also a notable example, but sometimes the .text segment has just code that will load an address into a register and use it that way, and it may never get registered. So there has to be some workaround to keep track of that, and all of these pointer assignments must be furthermore instrumented to keep track of the intended referent. Um, so in this case, where you have pointers P and Q, and you assign Q to be P plus 1, you have to keep track of the intended referent, whether or not it is within the base and limit window. Let me back up. If the P plus 1 assignment results in an address that is within this object's bounds, within the limit address, to make sure it is still valid. Otherwise, it will throw an exception because it would fail the runtime safety check. Now, again, this doesn't necessarily check whether or not the destination type for a pointer assignment is actually valid, depending on the compatibility of it. That is very hard to determine by the underlying bit pattern, or just let alone the address limits the memory footprint of an object. So type confusion is still permitted in many cases under this scheme. But it does allow more fine-grained runtime checks, in terms that even sub-objects within a class or a structure now have pointers assigned to them, and having this granularity extended down to them, to the sub-objects and their sub-allocations that manipulate them. So you can have tighter bounds checking in theory. So, to recap, type confusion may occur when casting through void, when casting to incompatible child types. Indirect causes involve calling any void function after an inline cast, and other developer errors. Any runtime or compile time safety check on a pointer assignment will fail when the intended referent is actually a valid object that is actually malicious, or when the intended referent is a void object, or when the intended referent is corrupted by another bug, say arbitrary 4-byte memory overwrite, A4BMO, or buffer overflow, or other forms of developer failure, perhaps improper sanitization, or initialization, or etc. So, there's been discussion on modifying the pointer type to allow metadata, so it could store within the pointer object bounds information, perhaps information about the base address, the limit address, or the size, and so on. The problem with altering this underlying type is that it would change the application binary interface. ABI for short. Think of it like API, the abstract programmer's interface. You know, the set of functions you can use within a library or a program. ABI is exactly the same, but it's with respect to programs talking to programs. Therefore, manipulating how the ABI would work would really complicate how programs work together and be impractical in the large scheme of things. So this, however, is still done actually in multiple very large projects. Browsers are the large culprit. I believe Chrome implements several types of pointers, self pointers, own pointers, and operating systems, VMs, and sandboxes implement these as well. And they have their own vulnerabilities in their implementations as well. There's another topic in this lecture to cover, is that all of these runtime memory safety checks fail in any multi-threaded application, especially well, especially when they fail to meet the following challenges. That the runtime type information on a shared object must be also edited atomically. Whenever the object itself is edited, its RTTI must also be edited atomically, and that's rarely ever done. The runtime safety check methods involving shadow memory, object tables, or pointer tables must also be updated atomically as well. And in general, according to the same paper we've been going through, none of these implementations are thread safe. None of them. So it is, in theory, easier to exploit type confusion vulnerabilities in any multi-threaded application, which is typically every application that attackers want to exploit type confusion vulnerabilities in, at least the most attractive ones. Type confusion is not just limited to C++. It is possible in any language with dynamic polymorphism and that performs any form of dynamic dispatch. There are examples in Python. Java is a big one. There are examples in Ruby on Rails, as well as several in PHP, and any other language that is essentially doing object-oriented dynamic polymorphism. And that is the end. Congratulations, you've finished the 3 lectures on C and C++ security, but the fun is only beginning.